So basically what I'm going to do, I'm not sure I'm going to cover everything. I mean, my goal is to have, after 2 presentations, to go from the theory to the applications. So I'm not sure that I'm going to finish today, but let's start. So the thing is that you generally know how to solve SDE and ODE of that type, where you have this equal 0. So that's your general ODE. And generally what's going to happen is that sometimes for some models you can decide to add a random term. And one particularly good example that he gave is the population model. Population model is said, okay, if you look at the population LT, and you have basically ODE like this, right? We know how to solve it, right? But sometimes this term N is a population and A is a growth rate. But sometimes in this model you assume that you know exactly the growth rate. But you can have a case where you say, okay, I don't exactly know. Let me put instead AT and T. The growth rate can depend on time, but it can still be deterministic. So the thing is that sometimes I don't know this. I know that it's just equal to a constant, a long-term constant, plus a noise, right? So this noise can define it like this, right? So if you put that in your differential equation, what you're going to have is something like this, AN plus gamma N, right? So you can see that from this is your typical differential equation, but now you have the addition of this term. And generally this term, I think you know what is a white noise, right? So generally a white noise is a random term. Generally you use a normal 0, 1 to model a noise. And if you have a term like this, it means that this one's going to be a normal, right? And because this one is fixed, it means that all your right-hand side is going to be just a distribution, a normal distribution. So now you cannot use your usual integration, to solve this problem, because on the right-hand side you have probabilities now, right? So this is why, you have to use probabilities for this. So, and what is generally the solution of this type of problem? It's to have a trajectory, right? Because the solution, for example, of this ODE going to be something like M0 e to the AT, right? So if you have a nice form, if A is constant, you're going to have an exponential form like this. But now A can be a random term, so you don't know exactly what you're going to have. But in this case, you're going to have a trajectory, right? And so the thing here is that we would like to model a trajectory, but the trajectory is not, that's a random variable, that's a stochastic process, basically, right? So, the new thing that you're trying to solve is exactly the same thing, but this time with this noise term. This time with the noise term. So that's exactly the same thing, but you just add, this noise term. But this is not yet a stochastic differential equation. Okay? Because the thing is that you need to know what is this noise term. Right? To understand this now, you need to go to, you can stop me anytime. It's supposed to be informal, right? So, the thing now, this is where you need to use probability. Because this one has a distribution, so you need first to understand the probability of this. And so you're going to have to define probability space as did in measure theory. The only difference is that, okay, you have a non-empty set, you have a sigma algebra, and you have a probability measure, okay? The difference with when you're talking, and this is called probability space. The difference with measure theory is that this P, you're going to add those two things, at least. So your probability of your entire space should sum to 1, to be equal to 1. Probability of the empty space is 0. And after that, you have all the A1, blah, blah, AN disjoint. And you want the probability of all of this to be equal to the summation of probability. So you basically have everything you have in measure theory, but this time you should have a maximum, the probability of the entire space equal to 1. Okay. So now you have the terminology is a little bit different because the element of omega, which is so you have, which is your space of all possible outcomes. The element of omega, of capital omega, called a small w, gonna be called the sample points. And every set A of omega gonna be called an event. So when you write, so basically you take your omega, W can be a lot of, anything inside. If you take a set inside, this is called an event. You take the probability of an event, it's written like P of A, basically. Okay. So the nice thing also is that in this case, you can model the information in your problem with your sigma algebra. Your sigma algebra gonna tell you exactly how much information you have. If I take and to see that, let me write a sigma algebra. So to see that, if you take the example of you suppose that your omega is a set of 8 possible outcomes of 3 compters. Okay, so you're gonna have a coin. You can have head or tail. You're gonna flip that 3 times, right? You're gonna have a set of possible outcomes, right? And your set of possible outcomes, you want to know if you know that the first outcome, if you know the first outcome, if you know exactly the first outcome, so all the set, the possible events, it's omega gonna be divided into 2, because you know what? You know that you're gonna start by head or you're gonna start by tail. Right. So from this, you can create those 2 sets. Because you know that the first one should be head. It's going to be the set head, 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 tail, head, tail, tail. I'm missing one. Yes.
Right here.
Head, tail, tail. Yes. Head, head, tail. The first one, right? Second one, same thing, tail, like this. Tail, head, tail, 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 head, and tail, tail, tail. Okay? So this is exactly the 8 possible outcomes when you know exactly the first one. Okay? So, now, what your sigma algebra is going to tell you is that if you know that you start with head, you know automatically that you know more in this, you're in this one, right? If you know that you start with tail, you know that you start with this one. So each time that you have an information, you know exactly where you are. Okay, so that's called solved by the information. And if you know the second outcome, then you know what? You know that this time you can define those sets. This set, you can define this one, HLA, this one, and you can define this one. So if you know the first outcome, you have only two sets basically where you can be. If you know the second outcome, you have 4. If you know the third one, of course you have all the possible events. Right? So the information that you have gives you an idea of the set where you can be. And this is generally with this one. If you know this, your sigma algebra is going to be 2b. I know nothing. I consider it can be anything. Or I consider, because I know the first outcome, I consider it can be head. Or I consider it can be tail. So your sigma algebra here, either is nothing, or it's everything. Or I have head, I know that I have head first, or I know that I have tail. Okay. Now, your sigma algebra here is going to be the first, because the first sigma algebra is in the second one, this one. You have head, you have tails, and now you have all of this, all the complements, all the unions of those ones. You see?
Yeah.
Because it needs to be a sigma algebra. So you have all this until AT. You have all complements. And after that, you can start to take the union of each of them. Okay? So this type of, and at the end, for each problem, you're going to have that your sigma algebra should be each time including in the other one. So it's like the degree of information that you have each time on your process. Okay. And it's generally called a filtration when you talk about stochastic process. So the filtration gives you an idea of your process, the information that you have about your process. Because the important thing is that when you have your, I try to visualize this using a simple tree. Okay, you have time 1, time 2, and let's say time 3. So let's suppose you have time 0. When you have time 0, you have no idea where you're going to be, right? You're going to be either in all of this or somewhere, you don't know. When you have time 1, at time 1, you already know if you were at H or at T, right? If you know that you were at H or at T, you know what's going to be the next one or what's going to be the other one, okay? Now, if you have time 2, you know that the first one was H and the second one was H or T, right? So you're gonna know if you're gonna be here, or if the second one was T, you're gonna know if you're gonna go there, etc. Right? So you refine your information, and if you are completely at 3, you know exactly what happened. You know exactly all those things. So this is how you can see the information. Okay, and that's a particular case, especially in finance. So they use a lot of filtration when they try to define the process. Is it clear?
Yeah.
Okay. So, all right. So we define the probability space. So on the probability space now, because the thing is that all of this is not observable. You have head, tails. It doesn't mean anything for you, right? The only thing you need, the thing you need actually to model your problem is generally a variable of interest. A variable interest in this case is like, what is the number of head that I have after 3 coin tosses? What is the number of tail? So you need to define a random variable, right? So after your probability space, you define a random variable. And your random variable has exactly the same definition than a measurable function. So your random variable, not going to write on, if you write that like this, a random variable going to be -1b, where this is also w, such that xw belongs to b. And you want this to be in your sigma algebra. Okay, so that's the formal definition of your random variable. So basically, your function is a function for omega to r, right? And what you're taking in omega is w. In this case, what is w? W is, okay. What is the number of head I can have? You can have w can be h, or w can be h, t, or w can be, so your random variable gonna map this with a number. In this case, it's gonna be 3, in this case, it's gonna be 2. But in this case, your w can be this, or it has the same number, it is this, right? But all gonna be mapped into 2. Right? So this is why you should write your random variable with a w. And generally, we do not write the random variable with a w. But that's why in layer theory, I mean, when you define that, you remember that you have this w. And so now, I mean, I don't really, do I need to go through all the expectation and those stuff? No, right?
I mean, it's up to you.
Yeah. Yeah, okay, so I'm going to skip that because, yeah, you know that from when you have a random variable, the only way to study a random variable is to look at probability density, to look at, yeah, let me write that here. So to study a random variable, you need probability, the distribution function. The distribution function. You can look at the moment, expectation, and variance. And this is generally the usual tools that you have for this. In stochastic process, one important thing is also you have the conditional probability, right? Which is a probability if you have two events A, B. So probability of A given B is equal to probability of A intersection B over probability of B. Okay? And the nice thing is that generally that's a typical question you have at CASA. People ask you, okay, how can I solve that, right? But you have a nice interpretation on using the probability space in the sense that if we suppose that our probability space is written as this, the sigma algebra and P, when you start to look at the conditional probability, you do not look anymore at the entire space, right? It means that here you suppose that a condition on B, so if I know B, what is the probability to have A? So if you know B, so it means that you know that you're already here, right? So your space is no more omega, your space is B, right? If your space is B, you can define a new sigma algebra, and this sigma algebra is going to be what? It's generally going to be all the sets C intersection B, such that C belongs to U. And you can define a new probability measure, which is over B. So your new probability measure is basically the probability, or your old probability, but over your probability of B. So when you work with conditional probability, you change your space. You go from this probability space to a more restricted probability space on B. Okay. So now, using this, you have expected conditional expectation. So you have conditional probability, now you have conditional expectation. It means what is the expected value?